All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, doing good. All right, so I know it's been a long wait, and so I brought everyone's exams today, and so if you haven't picked it up yet, you can go ahead and pick it up after class, just because I don't want people kind of congregating here during the lecture. So thank you guys for your patience. There was kind of a unique situation with this exam where I couldn't give it back, for a while, but that's been taken care of, and so you guys can pick up the exams after class today, and so just as always, so today will kind of mark the first day when you have your exams back, even though I know I graded it the previous week, and so please go through your exam, read the comments. If I make any mistakes, sometimes I make mistakes just adding up the points. And so if you notice anything on the exam, please let me know. I'm always happy to take a look at it again. And so remember, just a reminder, the course policies that you have a week after I give it back to you to kind of come up and ask for any regrades. And so that timer kind of starts today. Okay. All right. Right. Okay. And so the plan for today is we just have a little bit more to talk about in terms of muscle dynamics. And so I think we kind of left off kind of in the middle of something. And so we're going to finish that up. And then we're going to move on to our next big topic, which is human motion kinematics. Okay. So the next unit is actually it's quite fun. And in fact, it's one of my favorite topics of this class, just because it's very modern, which is kind of unusual for a class like this. Sometimes, we talk about methods that are kind of old, but we're talking about motion capture. And so how that works and how we can actually take that information, how to process that data, and turn it into something useful that we can use for biomechanics. And so motion capture hasn't been around that long. So to talk about something like this in this class, I think it's actually pretty exciting. Okay. All right. Can everyone, first of all, can everyone on Zoom hear me okay? I think the mic in the classroom still, okay, good. I think the mic in the classroom still buggy, and so I'm using my iPad microphone again. So hopefully that works well for today. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and finish up where we left off. Okay. And so what we were talking about last time was kind of a section called muscle force production. Okay. Okay. So last time we were here, we talked about this idea that the amount of force that your muscle can generate depends on quite a few different, conditions, right? And so not only does it depend on the size of the muscle, the dimensions of the muscle, but it also depends on its instantaneous length, the velocity at which it's contracting with, among other factors, right? And so we went over a couple key curves, like the force length curve and the force velocity curve, okay? So those were those two curves that we were talking about. Okay, and so just to kind of refresh your memory, we're not going to go through every detail of these curves again, but in general they look like this. And so for the force length curve, I'm going to stick to just the active force length curve. Okay. And so if you recall, there was a kind of it would rise up, and then there's kind of a region where it plateaus and then it comes down. Okay, so it's kind of almost like trapezoidal in shape, right? Okay, whereas the force velocity curve, looks something like this. So, we're not really going to concern ourselves with eccentric contraction. We're only going to look at kind of the right side of the curve, right? And so we're going to go from zero velocity. Okay. Remember, the maximum amount of force that your muscle can generate in, at least on the right side of this curve, is when there's zero velocity, right? And so we call that the isometric maximum. Okay. Okay. And then as the velocity increases, as the motion, basically the quickness of whatever motion that you're accomplishing increases, then the amount of force that your muscles can deliver at that velocity goes down. Okay. Okay. And so let me finish labeling these axes. And so on the horizontal axis for the left curve, the horse is muscle length. Okay. And the vertical axis for both of these curves is the amount of force that can be generated. Okay. Okay. So I think that's kind of what we spent the majority of the time talking about last class. Okay. But one thing that I didn't really mention about these curves, that these curves only really dictate general trends, right? Every muscle is different, and so the exact shape of these curves for each individual muscle is going to be different based on its characteristics. Okay. In fact, I think probably the more accurate way to say it is that not that these curves are different necessarily for different muscles, they're just scaled different. And so they have the exact same, trends, right? And so the force length curve is always going to have an ascending region. It's always going to have a plateau. It's always going to have a descending region. And then the force velocity curve will always have a maximum at the at velocity 0, and then decay downwards. Okay. But what's going to be different for each individual muscle is that they're going to be, scaled differently. So you're going to have kind of the plateau region, maybe wider, maybe taller, maybe shifted to the right or left. Okay. And the parameters that we use to scale these curves depend on, what we say is kind of 5 defining characteristics. Okay. And so that's kind of where we left off last Wednesday. It was talking about what these 5 characteristics are, and we're going to talk about what effect they have on these curves. Okay. And so another way that you can think about this is that these curves here that I've shown on the screen here are kind of a normalized or kind of non-dimensional version of these curves. Okay. And so if you've ever kind of experienced non-dimensional curves or scaled curves or normalized curves in your other courses, basically the idea behind a normalized curve is to show you kind of the general trends that are applicable to every single, instance of this. But then, when you want to apply this curve to, a specific instance or a specific application, you have to scale it appropriately. Okay. And those 5 characteristics that we're going to talk about are, what we're going to use to scale these curves. Okay. So I think we went over one of those characteristics last time. So we'll go ahead and review that today, and then we'll talk about the other 4 characteristics as well. Okay. All right, but that's just kind of just a recap from last. Are there any questions on this? Okay. All right, and so let's go ahead and start listing off those characteristics. Okay, so the one that we did go over last time was something called the optimal fiber length. Okay. So we call this LOM. Okay. And so what the optimal fiber length basically tells you is the length for the entire muscle, the optimal length for the entire muscle that produces the maximum amount of force. Okay. And so what really determines the optimal fiber length is basically how many sarcomeres or how many muscle units are connected end to end in the muscle. Okay. And so kind of an easy way to kind of think of this characteristic is that, is to kind of think about the distinctions between longer muscles and shorter muscles. Okay. Okay. Because no matter what muscle you look at in the body, the sarcomere, the little unit that has kind of the protein filaments, that has a fixed length, wherever you go in the muscle. Okay. What's different about each muscle is that each muscle has either more or less of these sarcomeres that kind of attach end to end. Okay. And so the muscles in your body that are considered longer, and so think about your longer skeletal muscles, like maybe your calf muscle, right? That's going to be a lot longer than the muscles you have in your hand, just because your hand muscles are a lot shorter than that. Okay. And so what we talked about is that, the longer your muscles are, the more sarcomeres are linked end to end. What that's going to do is that it's going to broaden your plateau region of your force length curve. Okay. It's going to lead to a broader plateau region, and it's going to shift it to the right as well. Okay. And so if we draw the force length curve, I'll give you kind of 2 examples here. One for a short muscle, one for a long muscle. Okay. And so for a short muscle, you might have a curve that looks kind of like this. Okay. Okay. Where the plateau region is kind of shifted to the left, and the plateau region is fairly narrow. Okay. Whereas for a longer muscle, you may have something that looks something like this. Okay. So the plateau region is shifted to the right, just because we have more sarcomeres kind of linked together, right? And it's also broader because the more sarcomeres you have kind of linked together in series, there's kind of a wider window of total lengths that you can use to still produce the maximum muscle force. Okay, so that's essentially what this characteristic kind of defines is kind of how much or how much region of maximum strength that you can produce, and that's kind of a direct correlation with the overall length of the muscle. Okay. Okay. Any questions on this? Okay. All right. So that's the first characteristic. Next one actually technically doesn't directly have to do with the curves, but it does affect how much force the muscle can generate. Okay. So the next one's called the pennation angle. Okay. So this typically has a symbol of phi naught. Right? So muscle pennation is actually something we kind of skipped earlier, just because I knew that we were going to come back to it later here, but then I forgot that I assigned a homework problem. so probably a lot of you are familiar with it already, just because you had to read the notes to answer the homework problem on it. But let's go over it together here. Okay. Okay. So the pennation angle here, it defines the angle at which the muscle attaches to a tendon. Okay. And so if you recall from our lectures on soft tissues, right, tendon is the structures in your body that attaches your muscles to your bones. Okay. And so the angle at which your muscle directly attaches to the tendon is going to have a big impact in terms of how much force it needs to generate to kind of act on that tendon. Okay. Okay. And so I'm using the term useful there, and I'm putting it in quotes because a useful component of the force, or a useful feature of a force is what I define to be one that actually goes into human movement. Okay, because we've already seen in our static analysis that a lot of times your muscles, or the force that your muscle generates, not all of it actually goes towards moving your muscles or moving your body. Okay. Just because of the way the certain muscles are angled in your body, sometimes you have a significant portion of that muscle that that doesn't actually contribute to movement, or it doesn't contribute to any motion or moment around a joint. Okay. And so kind of a very simple diagram of this, might be something like this. So let's say that you have a tendon that kind of attaches like this. Okay. And this is attached to a bone. And maybe you have a muscle that kind of goes at an angle like this. Okay. And so the fibers of the muscle are kind of running parallel to the lines that I've drawn here. Okay. Or this angle here, this angle is not theta. This angle is phi naught. Okay. All right. And if the motion of this tendon is defined as kind of going from left to right here, okay, that means if this muscle were to produce force, okay, so we'll call that FM, right? What we can say is that the amount of force that's on the tendons, we call that F sub T, this is equal to, in this case, FM cosine of the angle. And so in other words, what we're saying is that, the only useful component of the force is, only FM times cosine of that angle. Okay. All right, and then this tendon right here, we kind of skipped over the tendons, in our static analysis. Maybe the tendon is attached to the bone, at an angle like this. Okay. Right. It's kind of a bad picture. Usually the tendon doesn't attach in the middle like that. Maybe it's kind of more like this. Okay. So kind of the same idea as the attachment angle. Technically, the attachment angle that we were talking about was kind of, in static analysis was this one right here, but there's kind of another layer onto that. So, whatever angle that the muscle attaches onto the tendon itself, we also have to take that into account into our calculations. Okay. And that's what's defined as the pennation angle. All right, and the reason, a lot of your muscles are pennated is because your muscles are kind of, a lot of them are kind of compact into kind of a small portion of your body. So your deltoid muscle in your shoulder is a good example of this. And so your deltoid is actually quite a powerful muscle, but it's kind of limited in space. And so to kind of make use of that space, it actually makes heavy use of pennation to kind of put more muscle fibers in there, into kind of a small space. Okay. All right. Any questions on this? Okay. So that's pennation angle. All right, 3. This will affect kind of the, it'll affect a few different curves actually. And so 3 here is what we define as the maximum isometric muscle force. Okay, so we call this F0M. Okay, so this characteristic right here, you can kind of think of this as an upper limit, as the absolute upper limit that a muscle, in terms of the amount of force that a muscle can generate. Okay, and so under perfect conditions, okay, so you can kind of think of it like the absolute max amount of force that the muscle can generate. Okay. And so just based on the name right here, you can see that it happens in isometric contraction. So when there's 0 velocity, okay, and it's going to occur at the perfect optimal length and so on and so forth. Okay. All right. So what's interesting about this parameter here is that this is normally very difficult to measure because getting your muscle into the perfect kind of conditions, that's usually kind of very hard to achieve in practice. And so this maximum here is actually kind of more kind of more of like a theoretical maximum, right? And so if you were to kind of cut the muscle out and kind of isolate it and kind of measure it at its optimal length, this is kind of what you would get. Okay, and so in practice, this is not something that's easy to measure. Okay, and so what is typically done though is that we can estimate this based on instead the cross-sectional area of the muscle. In other words, we call that PCSA, or the physiological cross-sectional area of the muscle. Okay. And the reason we call it the physiological cross-section is that, whenever you take the cross-section of something, the exact area that you get depends on kind of the orientation of the slice that you take, right? And so if you take like so honestly, the best example I can come up, or the best visualization I can think about this is from cooking actually. And so if you have like a vegetable like the cucumber, right? If you slice it kind of perpendicular to the cucumber, you end up with kind of small slices. But if you slice at an angle, if you slice at a bias, then you're going to get kind of bigger slices, right? And so if you have like, maybe like here's your muscle, right? Imagine that it's kind of the same cross section, the same. Let me draw. I'll draw a better picture. Slightly better. Okay. And so if you take a cross section like this, right? The cross section is going to look different than if you took a cross section like that, right? And so the physiological cross section is, and so when you're talking about cross sections, you have to be kind of specific in terms of how you're taking that slice. Okay. And so for the physiological cross section, so the PCSA, we take our cross sections to be perpendicular to the muscle fibers. Okay. And so if you have any degree of tenation, or if you have any degree of, the muscle fibers not running parallel to the muscle, then you have to kind of adjust your PCSA according to that. Okay. Okay. And the reason for this is that, you remember we talked about, each muscle fiber is kind of, you can almost think of it like a big chain of sarcomeres, right? And so if you have several muscle fibers that are arranged in parallel, that's, another way that you can say that is you can have that much or that many sarcomeres that are kind of acting together for the muscle force. Okay. Okay. And parallel is kind of the operative keyword there. So if you have kind of two sarcomeres, and they're sitting next to each other, kind of in parallel, when they both contract at the same time, you can kind of add together their forces at any given point. Okay, and so we have this kind of I don't really want to call it a formula, just because it's not really based on kind of physical laws, but we have this relationship. And so the maximum amount of force, the maximum isometric muscle force that a muscle can produce, is you take your PCSA, okay, your physiological cross section, and then what you do from there is you multiply it by this factor called sigma OM, okay, where this factor right here, sigma OM, is the peak isometric stress that can be developed by a muscle fiber. Okay. Okay. And this does have a fairly known value. And so that's about 0.3 megapascal. Okay. So all of this here is just kind of a fancy kind of roundabout way to kind of tell you the difference in terms of thin muscles versus thicker muscles. Okay. So I'm going to focus on the description for thick muscles, and then you can kind of think of thin muscles as kind of the opposite. Okay. So thick muscles, those are going to have a larger cross-sectional area. These have a lot more sarcomeres kind of working in parallel. Okay. All right, question from the chat. So a question from the chat says, is the peak isometric stress the same for every muscle? Yes. And so that's measured in terms of how much force per area basically a sarcomere can produce. And so that is the same for every muscle. Mm-hmm. Okay. And so the more sarcomeres you have in parallel, that raises the cap in terms of the peak force that your muscle can produce. Okay. And so generally, and this is not true everywhere, but generally what you'll see in your body is that your muscles that are longer tend to be thinner, and your muscles that are shorter tend to be thicker. Right? So either long and thin, or short and thick. Okay. Okay. Which is not always true, but that's kind of the general trend. And the reason I kind of mentioned that is it makes drawing the curves a little bit easier. Okay. Or makes them stand out a bit more. Okay. So let me kind of show you the force length curve and kind of what that looks like under these conditions. Okay. All right, so for a thicker muscle, that's going to have a higher peak, right? And so if you were to draw kind of a shorter, thick muscle, it might look something like this. Okay, so that curve there is kind of for a thick muscle where kind of the peak is higher. Okay, this one also happens to be short, just because it helps the next curve kind of stand out. Okay, and so a curve like this would be kind of for a thinner muscle. Okay, and so you can see that the peak for the thin muscle is a lot lower. Okay. And this thin muscle also happens to be long. So you can see that, I've made the plateau region quite long, and I've shifted it to the right. Okay. Right. So these two generally they kind of generally go together in different parts of your body. Right? So the thicker muscles also tend to be quite short, and the thinner muscles, the ones that have to kind of span a longer length of your body, those often tend to be thinner. Okay. All right, so the thick muscles, they can produce a lot of force under the right conditions. It's just that they only have kind of a small window in which they can do that. Whereas the thin muscles can act optimally over a wider range. It's just that their peak is not very high. Okay. Okay, so let me also draw kind of the difference in the force velocity curve. And so for a thick muscle, again, we have kind of a higher peak. And so we have a higher isometric maximum like this. Okay. But because these muscles tend to be shorter, then they can kind of fall off very quickly. So you have something that looks like this. Okay. Whereas for the long, thin muscles, they may not have as high of a peak force, but they can maintain that force kind of over a longer period of time, or not time, but over a larger range of velocities. Okay. So that's kind of generally the trend that you see. Okay. But of course, the different muscles in different parts of your body have different demands. Some muscles can contribute a lot to weight bearing, and so those are going to be a lot stronger naturally. Whereas the muscles that are in your hand, maybe kind of they're short and thin, because there's not that much space in your hand, and your hand usually isn't lifting a lot of weight as well. But this is generally kind of the general trends that you see. All right, any questions on this? Okay. All right, so that's characteristic number 3. Let's go ahead and move on to characteristic number 4. So 1 and 3, I think, are probably the most important, but 2, 4, and 5 are also kind of interesting to look at as well. Okay, these are a little bit less, a little bit less standardized. And so number 4 here is the maximum contraction velocity. we call this V max M. Okay. And so just like the name implies, this tells you how quickly that muscle can contract. Okay. And so, you know, this particular parameter here, you know, depends on the number of sarcomeres. And so it's also kind of a function of the overall length of the muscle. Okay. So that's one factor that contributes to the maximum contraction velocity. But this parameter here, or this characteristic, also depends on whether your muscle is a fast twitch muscle, or a slow twitch muscle. Okay. All right. And so what's interesting about human muscle is that, you know, you can't really characterize a particular muscle as being all fast twitch or all slow twitch. And so, biomechanically, you know, there are differences between the two. But generally what you see in humans is that, you know, for any given muscle, you have kind of a combination, or kind of the fast twitch and slow twitch muscles are kind of intertwined in the human body. And different muscles have kind of different mixes or different ratios of fast and slow twitch. Okay. Okay. So that's kind of what makes it more difficult to measure. But if you look at other mammals or other animals, theirs are a little bit more segregated. So, you know, certain animals have certain muscles that are almost all fast twitch muscles, and some muscles that are almost all slow twitch muscles. Okay. And so if you look at poultry, you know, for a good example, so you know, I think we mentioned this briefly. So, you know, if you're looking at kind of the white meat, so that's kind of like you know, the breast muscles, things like that. Those tend to be more all fast twitch muscles. And the reason for that is because, you know, fast twitch muscles, the way they work, or the way they kind of generate kind of muscle force, you know, doesn't really rely on oxygen all that much. That's why they can kind of, you know, contract very quickly. And so the reason, you know, white meat kind of gets its name is because those, you know, those meats tend to be more lighter in color because they don't have as much myoglobin, which is kind of the chemical in your blood that stores oxygen. Whereas dark meat, you know, those do rely a lot on the myoglobin and the oxygen in order to produce that kind of, you know, that contraction within the protein filaments, and so those tend to be darker in color. Okay. So in other animals, it's more segregated, and so you can kind of see which muscles are, you know, very clearly which ones are fast twitch and slow twitch muscles. But for humans, you don't really get that as much, and so there's kind of a combination of both. Okay. Okay. So that's the contraction velocity, and so the last characteristic actually isn't technically a characteristic of the muscle itself, but more of a characteristic of the tendon that the muscle is attached to. And so the last characteristic here is the tendon slack length. Okay. And so its symbol, it's 0LS. S for slack length, and then the T here for tendon. Okay. So we've almost not talked about tendons at all. We've kind of acknowledged that they exist, but, you know, in terms of, you know, their biomechanical effects, we've been kind of largely ignored. Okay. But just like muscles, you know, your tendons are, you know, considered as soft tissue, and so they also kind of exhibit their own elastic properties. And so, of course, the elastic properties of the tendons are also going to affect, the amount of force that your muscle can produce and the speed at which it can contract and things like that. Okay. Okay. But tendons, molecularly are kind of very different than muscles. And so instead of modeling them as kind of a straight up spring, usually tendons are modeled more as kind of a non-linear spring, which is more rigid than a typical spring. Okay. Okay. And so the slack length is basically determines how much the spring or how much the tendons can stretch without being damaged, basically. Okay. And just like many of the other properties that we have here, we kind of have two extremes. Okay. We're not going to get into the specifics in terms of the governing equations that actually govern muscle force production. Just mostly just because of a time thing. But I did want to give you kind of trends that you can kind of talk about just in general. Okay. And so for tendons, we have kind of two categories here. We either have rigid tendons. Okay. So those are tendons where their slack length is fairly small. So those tendons can't really stretch or compress all that much. Okay. And then the other extreme is a more compliant tendon. So compliant tendon is more flexible, and it can actually stretch, sometimes actually quite a bit. Okay. Okay. And so the difference is the following. So for rigid tendons, rigid tendons is kind of what we've been assuming for the majority of the class so far. So rigid tendons, basically don't add anything, to the muscle force, and they don't kind of inhibit it. And so for the case for rigid tendons, basically your muscle force is basically transmitted to the joint or transmitted to the bone, without any issue. Okay. Okay. Compliant tendons, on the other hand, actually do have a strong effect on the amount of torque or the amount of moment that your muscle can produce. Okay, because what happens when you have compliant tendons is that when your muscle contracts, it usually does so at a fairly fast speed. Okay, if you have a compliant tendon, then before that muscle contraction kind of force gets transmitted to the bone, your tendon itself will kind of stretch along as well. Okay. And ultimately, what this is going to do is that it's going to delay that transmittance, right? And so almost think of it like you have a slinky attached to your muscle, right? And so you have your muscle that can kind of contract and produce force, okay? And then, but in order for that force to get to your bone or your joint, it has to kind of transmit that through kind of a compliant spring or slinky, okay? So your muscle might contract, and then your slinky will eventually contract as well, but there's going to be a delay, okay? Okay. And so actually computationally, if we were to actually solve the equations, if you have a compliant tendon, that actually complicates things quite a bit and actually adds another equation in our system. Okay. And so in addition to all the muscle curves that we've talked about, tendons actually have their own, force length curve as well. We're not going to go over it just for the sake of time, because I did want to get to motion capture today, but just know that it exists. Okay. Okay. Any questions on any of this? Okay, so let's summarize this before we kind of move on to motion capture. And so when you're talking about individual muscles, and you want to kind of compute the amount of force that the muscle can produce, there are 5 parameters that go into this, and technically 4 dimensionless curves that you need to look up as well. Okay. All right, so let's just kind of recap those parameters real quick, and then we'll recap the dimensionless curves as well. Okay, so for the parameters, we have 5 of them. Okay, and so the first one we talked about today was the optimal fiber length. Okay. 2 is the pennation angle. 3 is the maximum isometric force, which we said was a function of the physiological cross-sectional area. Okay. So actually for number 3 here, just because most of the time we don't measure the force, we just measure the cross-sectional area. 4 is the maximum contraction velocity. 5 is the tendon slack length. So that was the last one that we talked about. Okay. So those are the 5 main characteristics, or 5 main parameters that govern muscle force production. Okay. Okay. And so combined, what these parameters do is that they're going to scale, or they're going to affect, how much force or how we interpret these dimensionless curves. Okay, so these are the curves that we primarily talked about last time. Okay, so the first curve was the active force length curve, and so that's how much force your muscles can actively produce. Okay, and that's a function of its total length. Okay. 2 is the passive force length curve. Okay. And so what we saw last time was that as your muscle gets kind of stretched beyond, beyond a certain threshold, then the passive elastic forces will kind of kick in. Okay. All right, next we have the force velocity curve. And so that tells you how much force your muscle can produce at a given velocity. Okay. And that tends to go down as the velocity increases. And then finally, we have the tendon force length curve, which sometimes may play a big role if you have a compliant tendon, but that tells you how much force or how much passive elastic force the tendon can produce at a given length. Okay. Okay. So that's kind of the summary of kind of what I want you guys to take away from from muscle dynamics, is that you have all these different factors that can affect how much force your muscle produces at any given time. Okay. All right. any final questions before we move on to motion capture and kinematics? Question? Okay. All right, and so we've talked a lot about muscles this class, but that'll be it for now, for a while. Okay, so let's go ahead and move on to our next big topic here. So we're switching to a different set of lecture notes now, and so this is going to be human motion kinematics. Okay, so this is when things I think start to get a little bit fun, because we did our first half of the class was more on human statics. Then we kind of finished that up. Then we talked about kind of gait biomechanics and then muscle dynamics, which by their nature are just kind of mostly conceptual questions. And so now we're getting back into how do we actually do analysis? How do we actually do computations involving human motion? Okay, so this is the first step. Okay. So this unit here, this chapter here is going to be all about, how do we actually measure and how do we actually quantify what we define as human movement, okay? Okay. And so kind of the progression that we're going to go through here is probably going to be very similar to your dynamics course, where we're going to start with kinematics. So we're going to talk about how do we actually describe the motion, how do we quantify it, how do we measure it, and then we're going to move on to how do we actually compute the muscle forces that produce this motion. Okay, and so that'll be kind of inverse dynamics, which is going to be the next section. Okay, but first we have to talk about the kinematics. Okay, and so for human movement, the way that we kind of the standard way that we describe motion is through various joint angles and joint positions as a function of time. Okay. Because human movement is actually quite complex. So, for any given person, you have, in fact, dozens of degrees of freedom, right? And so, the many different ways that a human can move their body, even just for basic actions, even just for, just from walking from one side of the room to the other, involves kind of the movement of lots of different muscles and lots of different joints. Okay. And so, the kind of the standard way that we describe it is kind of the joint angles and joint positions. Okay, where in this kind of interpretation, or in this kind of model, we assume that each segment of the body is fairly rigid. Okay. Okay. Which for the most part is true, and so there is a little bit of compliance, especially for the body segments that don't have nearly as many bones, but relative to the amount of motion that you can produce, for your joints, it's a pretty reasonable assumption to say that each body segment is rigid. Okay, and so what we're concerned with then is kind of the relative movement or the relative position of each body segment relative to its neighbors. Okay. And so if we have kind of a, let's say that we have an arm here, okay? So your arm is primarily consists of 3 segments. I know technically your fingers can all bend as well, but when we talk about kind of the upper arm here, then the lower arm, okay? Then we'll consider your hand to be its own segment as well, okay? Right. And so we consider each of these to be kind of a rigid, a rigid link, okay? And then what we're going to measure here are, this angle here, this angle here, kind of the relative positions of the center of masses, okay? Right. So we're mostly concerned with, what's the kind of the relative, position of each body segment to the other, and how that changes with time. That's going to give us the move. Okay. And so I drew a fairly simple case here in 2 dimensions, but in reality, depending on how much flexibility you have to the joint, sometimes you need multiple angles or multiple degrees of freedom to kind of fully describe the relative positions. Okay. Okay. So for example, your shoulder is very flexible, right? So we basically consider it to be a ball and socket joint. And so you need 3 angles or 3 rotational degrees of freedom in order to kind of fully capture it. Okay. Okay, so we're going to talk about, how do we get these measurements and how do we quantify it? And it's going to involve a lot of algebra and a lot of math. And so definitely kind of buckle up for that. Okay. So let me just mention briefly, I don't want to get too much into it just because, we're running a little short on time, but kind of the whole idea behind these kinds of techniques, date all the way back to actually kind of the 1800s. And so that's when kind of not motion capture, but motion video, really started to become a thing. So one of the first guys to do this is his name is Edward Muybridge. And so in the 1870s, he was one of the first people that's credited with kind of taking a video of a horse kind of galloping down a track. And what he was able to do is he was able to kind of keep pace with the horse and kind of get a very nice kind of stationary kind of image of a horse galloping. Okay. And then based on his video and based on his analysis, that was kind of the first time that we actually start to kind of start to get some notions of how do we actually compute these muscle forces, how are the joints related to each other, and that's kind of the birthplace of a lot of this a lot of this theory. Okay. And of course that those techniques kind of evolved, and kind of the most modern version of that today is motion capture. But people have kind of experimented with kind of wearable accelerometers, wearable gyroscopes to kind of measure these things as well. Okay. All right. But of course, the most modern version of this is called optical motion capture. Okay. And so optical motion capture, I like to think of it as a fairly straightforward problem. And so I think it's fairly straightforward to kind of understand kind of the goal of motion capture, but with a lot of practical challenges. Okay. So actually kind of implementing it in practice is more challenging than it seems. Okay. Okay. And so the whole idea with motion capture is to kind of attach these almost kind of like reflective markers or kind of trackers on a person's body, and you place them in kind of strategic locations, and then you track their positions over time using multiple cameras. Okay. Okay. All right. And so if you've ever seen any kind of mocap or people doing this in practice, probably I think probably most common or the most common place that people have seen is for movies. Okay. And so computer graphics, video game graphics have kind of come a long way. And so a lot of times they use motion capture to really kind of get a realistic movement for the movies. Just because sometimes it's very difficult to kind of mimic that purely just using computers. Okay. And so what you'll probably see is that you'll probably see a person going through a typical motion, maybe like running. Okay. But they're kind of wearing this kind of all black suit. And then on that black suit, you have kind of all these little markers. Okay. Okay. They're seemingly kind of all over their body, right? And so, as they kind of go through motion, then the positions of the trackers are marked. Okay. And you might have seen kind of the follow-up image of like on a computer, you see kind of a computer model of like of like Buzz Lightyear or Woody or something like that, kind of mimicking that same motion. Okay. Okay. And so what we're going to talk about is, how, first of all, how many markers you need, and how do we take that marker data and actually, convert it to actually useful data for biomechanics. Okay. All right. And so the bare minimum, right? So for a particular body segment to kind of track its motion through time, you need at least 3 non-collinear markers. Okay. And by tracking a body segment, what I mean is to track its not only its position, right? And so the position of its center of mass is important, but also to track its orientation in space. All right. And so for a given body segment, let's look at the arm again. Okay. And so per segment here, so we have two, well, I'm not going to count the hand because the hand is usually kind of hard to measure. But for the upper arm and the lower arm, you need at least three markers per segment. Okay. And they have to be non-collinear, so they can't all be in a straight line. Okay. Okay. But sometimes, if you're kind of really strategic and you put certain markers in strategic locations, sometimes you can get away with less. Okay. And so, for example, if you have kind of two segments that are kind of connected right here, you can put kind of one marker right at the elbow, okay? Okay, so right at kind of the interface or right at the joint between two segments, and that one marker can be shared between the two. Okay. And so basically what's being tracked, as a function of time is you can almost think of it kind of like a triangle, triangulated position of each body segment. And so you need three markers in order to do that. Okay. That's the bare minimum, but that's kind of the best case scenario. In fact, practically a lot of times you actually have more than three markers per segment, based on a lot of practical. So we'll kind of stick to just kind of the base theory for now. Okay. All right. So in addition to, the markers are kind of the first step to motion capture. The other piece are the cameras. Okay. And so in most cases, you're going to need more than one camera. In fact, sometimes even more than two or more than three cameras in order to capture, to get a good capture of 3D motion. And the reason for this is that, human motion takes place in 3 dimensions, right? But a camera is kind of limited in that it can only capture a 2-dimensional image, right? And so in order to kind of reconstruct a 3-dimensional motion, you need several cameras, at the very least 2 that are perpendicular to each other, to capture kind of the full 3-dimensional position of each marker as a function of time. Okay. Okay. Right. And of course, there's some processing that kind of goes into this, right? And so there's some kind of fairly sophisticated computer code that kind of takes, that you can almost think of it as kind of almost like reconstructing a 3D scene, from cameras at certain different angles. Okay. So let's do just kind of a very simple example. So let's look at a 2-camera setup. Okay. Okay. So we'll call this one here camera 1. Okay. And we'll say we have another camera that's viewing perpendicular to it from right here. Okay. And so let's say that we have a subject right here, and we're just going to look at the position of one motion capture marker. Okay. Okay. All right. In addition to that, let's say that we have some reference point that's kind of fixed to the ground. So let's say that we have kind of a point that's on the ground here, which is going to act as our reference point. Okay. And so let's look at the images from the 2 cameras in terms of what they're showing. Okay. This is camera 1 and camera 2. Okay. Let's assume, for instance, that the cameras are oriented in a way where the reference point appears in the bottom left of each of these cameras. Okay, so they kind of act as the origin for our measurements. Okay, and the point, maybe appears in the one mocap point appears in kind of 2 places, in each camera. Okay. Okay, and then based on its position relative to the reference point, let's say that this here is 10 centimeters. Okay, this distance right here is 30 centimeters. Okay, so you can almost think of that as kind of the X and Y, components of that point, okay, relative to the reference point. Okay. And then in the second image, you can see here that the dot is kind of 50 centimeters to the left of the mocap marker, or the mocap reference point, sorry, and it's 30 centimeters off the ground as well. Okay. Okay, and so based on these measurements here, let's kind of write out what the XYZ positions of this point. Okay. Okay. And so, of course, we have to define, what direction is the X direction, what direction is the Y direction, and the Z. Okay. And so, just for now, let's assume that the X direction is this way. Okay. So I'm gonna draw it relative to the reference point. And so let's assume that the X direction is this way. Okay. We'll assume that the Y direction is this way. Okay. And the Z direction is going to go up and down. So that's the vertical direction that you can't see, because we're in kind of a bird's eye view here. Okay. And so this tells us that if the X direction is going downwards from this reference point, okay, that means the camera view that gives us the best vantage point of that X direction is camera 1. Okay. That means this 10 centimeters, that 10 centimeters is its X position. Okay. And then we can make that same argument for the Y direction as well. Okay. So since the Y direction is kind of going horizontally to the right, then the camera that has the best view of that dimension is camera 2. Okay. And then this measurement right here, the 50 centimeters, that's considered its Y direction. Okay. And then from both images, you can see that our point is 30 centimeters off the ground. And so that would be our Z component. Okay. And so its X, Y, Z positions here is going to be 10 centimeters, 50 centimeters, and 30 centimeters. If we had just one camera here, if we had just only camera 1, it would be impossible to tell the Y position of this point, because that's the direction that's kind of perpendicular to the camera's view. Okay. And so at the very least, if you're going to track 3D motion, you need 2 cameras. But what we're going to talk about next time is that a lot of times you need more than 2 cameras. And in fact, the more cameras that you have, the better. Because depending on how you're moving around, depending on the positions of your limbs, you may block a marker for temporarily, or one may go out of frame, for instance. And so having more cameras makes your reconstruction a lot more accurate. Okay. All right. Any final questions on this before we wrap it up for today? Okay, all right. And so if you haven't picked up your exam and you're in class, you can come pick it up. If you're on Zoom, I'll bring the exams on Wednesday as well, so you can pick it up there too. Okay. All right. So thank you guys for coming today. Hope you enjoy the rest of your day, and I will see you on Wednesday.
Safe. No, you're good. you want to look through these ones?
Your works like.
Oh, I think you're right.
Oh, yeah. This shows it. But then someone here. Thanks.
Tell us about the project groups and everything today.
I'm doing Wednesday.
So is it like we have to make the groups? Or
Yes.
We have to make the groups?
Yeah.
And the topic as well?
Yes. Yeah. So we'll talk about more on Wednesday, but yeah, I'll let you guys pick your own groups and then pick the topic.
Okay.
Yeah.
Great. Thank you.
Yep.
You have to return this to
Oh no, you can keep it.
Oh, so we have to keep it.
Yeah.
You don't need to return.
Yeah. No, it's all yours. Yeah. Yep. All right, Zoom. Any final questions before we wrap it up?